It's a pleasure to introduce my colleague from Stony Brook, Blaine Lawson, who's going to speak to us now on Lagrangian potential theory and Lagrangian equation of Monge Ampere type.
Oh, thank you very much, Simon. So, what I want to talk about today is something that's joint work with my long-term colleague, Rhys Harvey. And it's in a way something that we've known for many years, but somehow it never got sort of elucidated in all the kind of general results we were concerned with. And so I'd like to sort of give you the spirit of it today, and it's something that, among other things, is certainly related to symplectic geometry. Now, symplectic geometry is such a profound subject these days, with so many great people working on it. I don't think it's going to have a big effect. But it's nevertheless, I think, something that one should know. And so what I'm hoping to do today is to give you, anyway, a view of what goes on. So the outline is that first I'm going to give you some background so that you'll see our point of view. And then I'm going to just look in what happens in Euclidean space, because a lot of what happens there easily translates to general manifolds. Okay? And then I'll give you some idea of what happens for, in particular, on Grumoff manifolds, symplectic manifolds with this Grumoff metric. Okay? So the first thing is generalized potential theories. And the idea here is quite general. Let's suppose we start in Rn with a differential equation, which is just a function on the second derivatives, and it's constant coefficients. It doesn't change with time. I mean, with space. Then there's always an associated potential theory. And it's based on the sub-solutions, the things that satisfy this inequality. But you want these to be satisfied in some generalized sense. Okay, and to be precise about that, I'm going to use viscosity theory. And I'll make that more clear as we go along. Okay, so now, the kinds of theories that I want to talk about today are, in some sense, very restrained. There are things that I like to think of as geometrically based theories. So suppose you start with a compact subset of the Grassmannian of p-planes in Rn. Okay? Then you can look at the following cone, the set of all symmetric n by n matrices that have the property that their trace on every p-plane in this family is greater than or equal to 0. Okay, now that gives you a certain differential subequation. If you're given a C2 function, then you can say it's G plurisubharmonic if the trace of the second derivatives, the Hessian matrix, on every G plane is greater than or equal to 0. That's simply the statement that the Hessian matrix lies in this convex cone. Okay? And you can notice that if you have a C2 function which satisfies this plurisubharmonic condition, then in fact it's actually subharmonic whenever you restrict it to one of these affine G planes. Okay, and it turns out, and I'll mention why this is true, it's also true that if you restrict it to any minimal G manifold, that is a minimal submanifold, all of whose tangent planes lie in G, it is also subharmonic with respect to the Levi-Civita Hessian, or Laplacian, I mean. Okay, so now there's a notion of harmonic, and a C2 function is said to be G harmonic if its Hessian lies in the boundary of this cone. We've got this big cone, and the equation is to be in the boundary. Okay, so let me amplify this with some examples. So the very simplest kind of G you can imagine, and the only one in dimension n, is where you take the whole plane Rn in Gn of Rn, okay? And, well, PG is just those matrices whose trace is greater than or equal to 0. And so U is G plurisubharmonic if and only if it's subharmonic, right? Now, when you apply viscosity theory, the subharmonic functions are no longer C2, and exactly what you get are what we all know to be the standard theory of plurisubharmonic functions. You notice that G harmonic means precisely that we're looking at harmonic functions. And so this simple example is classical potential theory. Now, the next case is a little more interesting. I want to look at the entire Grassmannian of lines in Rn, okay? And in that case, this cone is the set of n by n matrices, symmetric matrices, which are greater than or equal to 0, right? The non-negative symmetric matrices. And so something is G plurisubharmonic if and only if the matrix of second derivatives is non-negative, and this is the theory of convex functions. And when you use viscosity theory, that you really do get the full notion of convex functions in any one of the many definitions of convex that are all equivalent. Okay, and notice that something is G harmonic if, first of all, it's convex, but the determinant has to be equal. The determinant of the Hessian has to be equal to 0. That means it satisfies the homogeneous Monge Ampere equation. And this is clear because all the eigenvalues of d squared u are greater than or equal to 0, but to be in the boundary, you have to have at least one of them equal to 0. And that's guaranteed by the determinant being 0. Okay? Now, the next example is a little bit more interesting. You look at G to be the complex Grassmannian of one plane's complex lines in Cn. And that's a subset of the Grassmannian of real two planes in R2n, okay? And now, I want to note that the symmetric n by n matrices, the symmetric 2n by 2n matrices have a natural decomposition into the Hermitian symmetric and the Hermitian anti-symmetric parts. In particular, if I give myself a 2n by 2n matrix, where I'm considering Cn to be R2n, and I let J be the matrix which is multiplication by I, then I can write A in this, let's see, what do I do here? I can write A this way, clearly, and I identify them as asymmetric and a skew symmetric, and you see that the symmetric part commutes with J, and the skew symmetric part anti-commutes with J. Okay? And so now the PG in this case is simply the following. You give an A, you take its Hermitian symmetric part and ask it to be greater than or equal to 0. The Hermitian symmetric part, the eigenvalues will appear in pairs on complex lines. And so I'm taking a kind of real view here. And again, when you look at the Hermitian, when you look at the equation, function U is G plurisubharmonic if and only if this symmetric part of the Hermitian matrix is of the matrix is greater than or equal to 0, and that's simply the notion of plurisubharmonic functions in several complex variables. It's another way of saying it. And when you apply viscosity theory, you really do get all the plurisubharmonic functions that you're used to seeing in several complex variables. And when you look at the harmonic theory, you get precisely the plurisubharmonic functions that satisfy the complex Monge Ampere equation for exactly the same reasons. Okay. Now, oh yeah, and I want to talk about, so why we were interested in all of this. It's because it got started anyway because of calibration. So if you're given a constant coefficient calibration, that's a p-form whose restriction to any oriented p-plane is less than or equal to the volume, then you can define G to be those p-planes where you actually get equality. If you take phi and multiply it by the right factor, there'll always be at least one plane where this is true. And the G submanifolds are homologically area minimizing, and what's interesting is that the G submanifolds and the G plurisubharmonic functions are somehow dually related. Okay, this is a different story, but it is interesting. So, you know, the calibrations that, for example, could come up are the divided powers of the Kähler form, the special Lagrangian calibration, the associative calibration on the octonions, and so forth. All right, so now I want to talk about the Lagrangian potential theory. So here, you probably know at this point, I'm going to let G be the set of Lagrangian planes in Cn. Okay? And so this is contained in the Grassmannian of n planes in R2n. R2n is identified with Cn, with complex structure J. And I remind you, Lagrangian means that that when you take J of the plane, you get something completely orthogonal to it. And then P log is then, again, the set of 2n by 2n symmetric matrices such that the trace on every Lagrangian plane is greater than or equal to 0. Okay? So this gives us a notion of Lagrangian plurisubharmonic. Lagrangian plurisubharmonic. And you notice that Lagrangian plurisubharmonic means that it's subharmonic on all affine Lagrangian planes. And it's also, it turns out, it's also M subharmonic on every minimal Lagrangian submanifold. Now, the reason for that is this little exercise. If you take d squared u, this is a function in R2n, and you restrict it to a submanifold and take its trace, it falls into two pieces, the tangential and the normal part. The tangential part is the intrinsic Laplacian for the metric induced on u, and the normal part is just the mean curvature vector. And so if you have a minimal one, they're the same. Right? If m is minimal, then this is just the... And so if this is always greater than or equal to 0, when you restrict it, it's greater than or equal to 0, it's subharmonic on m. Right? Okay, now I want to talk about what happens when you try to make these things a little bit more, a little bit less differentiable. So I'd like to extend this notion to non-differentiable functions. And in fact, what I want to consider, oh, well, yeah, I should say, I'm going to use viscosity theory, as I've said, and this is a theory that has been around for several decades. It was started by Crandall, Ishii, Lyons, and Craig Evans, and there have been many, many people who've worked on it, and it's had many, many successes. So I want to start with the following. Suppose I take a domain in Rn, then I want to look at the set of all functions on the domain which are allowed to have the value minus infinity, okay, but not plus infinity. But I do want these functions to have negative poles, and I want them to be upper semi-continuous. So it's a pretty vast set of things. Now, Now, in order to get differential equations into this, we have to have some sort of test function which is actually differentiable, like in distribution theory. So here, a test function is the following. A test function is well, if I have a point, I fix a point in the domain, then a test function at that point is a C2 function defined in some small neighborhood of the point with the fact that it's greater than or equal to my upper semi-continuous function in that neighborhood and is equal to it at the point. Okay? So I have my upper semi-continuous function, and I have this nice C2 function which lies above it and meets it at the point in question. Okay? Then a function is said to be log plurisubharmonic in this sense if for every point in the domain and for every test function at that point, the second derivatives of this test function lie in this P log. Okay? Now, oh yes, and I'm going to let P sub log of omega be the set of these. So now, there's something to note, and that is that test functions may not always exist. You could have a point, for example, where the function is equal to minus infinity, and you can't do that. And it also could simply be that there are no C2 functions that actually lie above it and are equal to it. And this is an important fact in the theory. So let me try to explain this. So let's take the function which is just the absolute value of the first coordinate u1. Okay, this is so this is something which is harmonic away from where x1 equals 0, and it's convex actually away from x1 equals 0, although you don't think of it as convex, it's just linear. But no test functions exist along the hyperplane where x1 equals 0. Right? I mean, this is something which is like this, and so you can't get something smooth above it, which is actually equal to it at that point. Well, yeah. On the other hand, well, so hence the conclusion is that this is actually a convex function everywhere, and in particular, it's log plurisubharmonic in the viscosity sense. On the other hand, if I take minus the absolute value of x1, then there are lots and lots of functions which are test functions, because now it's upside down. And I don't know if that's visible, but when you turn it upside down, there are lots and lots of C2 functions that are above it and equal it at the point, and so you can just take x1 minus x1 squared, and then you get a function whose Hessian matrix looks like -1 and then lots and lots of zeros, and that's definitely not in this cone. Okay? So this is somehow the way the theory works. Now, once you have this, it turns out that there are a lot of great properties. I mean, if you have two functions which are in this set of P log, then their maximum is in there. This set is closed under decreasing limits. It's closed under uniform limits. And if you give yourself a family contained in P log, which is locally uniformly bounded above, then you can take the upper envelope of that family. You take the soup over everything in the family at each point. That gives you something which is not upper semi-continuous, but you can take its upper semi-continuous regularization. And that's always, again, in this space. So this is the Perron method, right? This is something you've seen over and over again in subharmonic theory. Okay, so now on the other hand, we had this definition, and we started off with C2 plurisubharmonic functions, and one needs to know that the C2 functions don't evaporate when we go to this new definition, and that's true. C2 plurisubharmonic functions are viscosity plurisubharmonic functions, log plurisubharmonic functions. And another thing to observe is that the log plurisubharmonic functions are actually classically harmonic, because you can write Cn as a Lagrangian plane plus j of the Lagrangian plane. And now you know that the trace on the Lagrangian plane is positive, and that on its complement is positive, so the trace on the whole thing is. You apply that to test functions, and they're now subharmonic in the usual sense. Okay, now I want to say something about the dual equation. So the dual equation is gotten by taking the interior of the given equation, take its complement, and take minus it. And if you do that in this case, you get the set of A's such that the trace of A on some Lagrangian plane is greater than or equal to 0. Sort of the opposite of being positive on all such planes. And then something is log harmonic, a function is log harmonic if it's log plurisubharmonic, and minus it is dually log subharmonic. In other words, the minus d squared u lies in P in this space, okay? That's simply saying, another way of saying this is that u is both a subsolution and a supersolution, because when you take, if you take minus u, that's u, then this is essentially the complement of the upper cone, and that's what you mean by a supersolution. Okay. Now I want to say a little bit about log convex domains. So suppose you start with a bounded domain in Cn whose boundary is smooth. Then I say that the boundary is strictly log convex if every point has a defining function which is strictly log convex. Now, defining function is simply you take the point and you take a neighborhood of the point and a smooth function which is 0 on the boundary and has non-vanishing outward pointing gradient at all points. So it's negative inside and positive outside. And to say that it's strictly plurisubharmonic simply means that its trace on every Lagrangian plane is strictly positive, okay? So, but this can be also characterized in terms of the intrinsic geometry of the domain, namely, you take the second fundamental form of the domain with respect to the interior normal, and yeah, the interior normal. And you ask that the trace of the second fundamental form on every tangent Lagrangian plane be strictly greater than or equal to 0. So this is something which is, a property of the geometry of the boundary of this domain. Okay. So given all that, we can do the following. Given any domain in Cn bounded with a strictly convex boundary, smooth boundary, which is strictly log convex, then for every continuous function on the boundary, there exists a unique function continuous on the closed domain with the two properties you expect. It's log harmonic in the interior and equals phi on the boundary. Okay? So existence and uniqueness hold. Okay. So this means we have lots of these things locally. I mean, any convex domain is log convex. Okay? So the question is there a polynomial differential operator whose solutions are log harmonic? So is this actually given by some polynomial operator? And it's not always true, even in these geometric cases, that you can always write down some sort of operator, but the operator has no isn't given by a polynomial. You can't differentiate it. So it would be nice if this were true. And so I want to go back to this thing that we did before. So you take the 2n by 2n symmetric matrices and decompose them under un. So the first thing that happens is it decomposes into the Hermitian symmetric and the Hermitian skew symmetric parts. And then the Hermitian symmetric parts themselves decompose into multiples of the identity and the traceless symmetric parts. So if you start with an A, which is a 2n by 2n symmetric matrix, it first of all decomposes, as I said before, into this piece which commutes with A and that which anti-commutes with A. And then the one that commutes with A can be written as the appropriate multiple of the identity, namely the trace over 2n, and then the Hermitian symmetric part minus that, which is the traceless part. Okay, now this is a complete reduction under the unitary group. And the basic fact is that the log analysis, everything that I'm going to talk about, is completely independent of the traceless Hermitian symmetric part. It plays no role. So this is easy to see, but let me prove it for you. So suppose I have a 2n by 2n symmetric matrix, which is symmetric and of trace 0. Symmetric and of trace 0. And I take a Lagrangian plane W. I can choose an orthonormal basis for W, E1 through En, and then the trace of E on W is simply the sum of E applied to EK inner product with EK from 1 to N. But multiplication by I is an isometry here, so I can replace capital E, small e, EK, inner product with EK by putting J's in front of them, right? J is an isometry. So I can do that and then divide by a half and I get the same thing. But now, because this guy is in the symmetric part, I should do this, here it is. J commutes with E, so it comes down here. I can put the J on the inside. Now you're looking at the trace. And that is 0, because it was in the trace 0 part. So if you take these guys and take their trace on Lagrangian planes, this part is always 0. It plays no role. So this is kind of interesting. If you go back to the complex Monge Ampere equation, it's all about the Hermitian symmetric part. It's exact, and if you look at the skew symmetric part, as I've defined it, it plays no role because its trace on every complex line is 0, right? The skew symmetric part its trace on every complex line is 0. So now, in our case, if you look at what I want to call the Lagrangian part, which is the part that's a multiple of the identity plus the skew, this plays a central role in log analysis and in the Lagrangian Monge Ampere equation, but the traceless Hermitian part is invisible to this theory. So there's a kind of duality here between the complex Monge Ampere equation and what I'm going to discuss as the Lagrangian Monge Ampere equation. So what is the Lagrangian Monge Ampere equation? Well, suppose I have something which is Hermitian skew. That is, it anti-commutes with J. Okay? So if I have an eigenvector E with eigenvalue lambda, then JE is also an eigenvalue with eigenvalue minus lambda. So that is to say that the eigenvalues for a skew symmetric part appear in plus and minus pairs. this symmetric matrix looks like this. The eigenvalues are lambda 1 minus lambda 1 down to lambda n minus lambda n. And it's really hard to, you can't really determine which is which, but so if you want to make this more canonical, you can just order this so that all the lambdas are greater than or equal to 0. Okay? And you can see that if we make this assumption that all the lambdas are greater than or equal to 0, that the trace of this skew-symmetric part on any Lagrangian plane is greater than or equal to this maximal negative value, which is minus lambda 1 through lambda n. Okay? So now, suppose we have a 2n by 2n symmetric matrix, and I have a Lagrangian plane W. Then if I take the trace of A on W, as I've just shown you, the Hermitian trace, the symmetric traceless part goes away, and that's just the trace of this Lagrangian on W. And now the trace is linear, so the Lagrangian part comes out. Of course, the trace of the identity on this is n, so it comes out as trace of A over 2. And then I'm left with the trace of the skew-symmetric part, which I've just pointed out to you is greater than or equal to mu is now m over 2, minus the sum of positive eigenvalues. So here's where lambda 1 through lambda n are the non-negative eigenvalues of the skew-symmetric part. Okay, so this is all fairly straightforward, and so now what are you going to do with it? So I now see that I always have this inequality, where, as I've just said, and so that means that the trace of A restricted to any Lagrangian plane is greater than or equal to 0 if and only if this quantity, the trace over 2 minus the sum of the positive eigenvalues of the skew-symmetric part is greater than or equal to 0. Okay? So let's consider the following operator. I can't really differentiate between, there's no way of sort of finding out where the positive and negative eigenvalues are in some sense. So what you want to do is to go over all of them. So I'm going to take a product. This mu is always fixed, of mu plus and minus lambda 1 up to plus or minus lambda n, and I go through all the signs, right? So that's 2 to the n. That's 2 to the n factors, right? Linear factors here. And notice that this guy in red, it's a polynomial in mu, and the coefficients are polynomials in the lambdas. But because of the way we've sorted it out, if you send lambda I to minus lambda I, nothing changes, and if you permute the lambdas, nothing changes. So this is going to be a polynomial in mu where the coefficients are symmetric functions of lambda 1 squared through lambda n squared. Okay? And that means they're really polynomials in A. They're really polynomials in A. So this is a polynomial differential operator. And now the thing to point out is that I have this thing called p log, and so remember that this is a certain convex cone in the symmetric matrices. So let's first of all throw away all of the, well, let's look at the set of matrices for which this operator is strictly positive. This is going to fall into several components, just like the determinant. If you ask where is the determinant positive, there are many, many components. I want to take the component that contains the identity. I take the component that contains the identity matrix, and I take its closure. And that's exactly p log. So this is very much like the Monge Ampere equation, where you take where the determinant is positive, you take the component that contains the identity, and you take its closure, and that gives you exactly what you want for either Monge Ampere equation. Okay, so notice that now a log harmonic function is simply a viscosity solution of the following set of equations as before. First of all, it has to be log plurisubharmonic, and the Monge Ampere operator has to be 0. The Monge Ampere operator has to be 0. Okay, so now it's nice to have a more invariant definition of this. So there are two of them. The first one is you take this A and you take its Lagrangian part on the right, and you will allow the Lagrangian part to act as a derivation on the nth exterior power of R2n. So you look at that. So it's a derivation whenever it sees a simple vector. It acts as a derivation in the usual way. And then this Monge Ampere operator is simply a factor of the determinant of that equation, of that operator. And it's a standard, it's a universal determinant. But the definition I like concerns spinors. So let me give you a definition from that point of view. So I start again with A, and I take its skew symmetric part, which I'm going to call B, right? Now B is, as I pointed out, can be diagonalized with plus and minus. So let me put all the plus eigenvalues at the top and the minus at the bottom. Now, I can take the absolute value of this. That's a reasonable thing to do. I square the matrix, and then I take its square root, right? This is standard spectral theory, if you like, on finite dimensions. And then I multiply by J. And what I get is the skew symmetric matrix with lambda and minus lambda. In other words, my A gives me a 2 form on R2n, which I'm going to call capital B, or bold B. Okay, so I now have a 2 form in R2n, and I can consider the 2 forms in R2n as part of the Clifford algebra in R2n in a completely canonical way, as part of the Clifford algebra. Now, the Clifford algebra in R2n has a nice irreducible representation, and in fact, it's given precisely by taking one of the ways you can do it is you look at all the 0 Q forms, okay, and that gives you something which is a representation of this Clifford algebra. B acts by Clifford multiplication, and so I claim that M log is nothing but the determinant of mu times the identity plus I bold B acting by Clifford multiplication on this irreducible spinor space. Okay? So, I mean, it's not, so you've got a lot of factors here, but but from this point of view, it's actually pretty straightforward, and this will be, make sense on manifolds too. Okay, so in the little time I have left, let me say how this goes over to manifolds. So, I mean, it goes over to in quite a lot of generality, but in particular, it goes over to what I'm calling Grumoff manifolds. And a Grumoff manifold is a symplectic manifold, x and omega, equipped with an almost complex structure that has the following 2 properties. J preserves it, and when you look at omega of JVV, that should be positive definite symmetric form, positive definite quadratic form. okay? So then it actually gives a Romanian metric, and that Romanian metric satisfies these nice conditions on the manifold. So the interesting thing, one of the many interesting things in this wonderful paper of Grumoff, where he introduced pseudo-holomorphic curves and proved all sorts of amazing theorems, was that every symplectic manifold has such a metric. So let's just do that, okay? Let's take that metric. And I want to point out that if you do, then if you look at symplectomorphisms, symplectomorphisms preserve the quadratic form and the Lagrangian submanifolds, and you take the symplectomorphism and you can push forward the almost complex structure and therefore the metric. And so in some sense, these things get translated along. All right, so now what we need to do to make things work on a Grumoff manifold is to use the Romani and Hessian. So I remind you what that is. It's a quadratic form on the tangent space given as follows. This should be, U should be an F in this case. Given a function F, which is C infinity, and given a pair of vector fields V and W, the Hessian on V and W is simply, first of all, you take the derivatives, W of F, and then followed by V of F, and then you subtract off the first order derivative where del VW is just a Levi-Civita connection. Okay, so del VW. And this is something which is symmetric because when you interchange V and W and add them together, you get 0. You get the Lie bracket in two different ways. Okay, so this is actually something which is a canonical Hessian, and it gives us a decomposition of J2, the two jets on the manifold, into the real numbers. That's just the value of a function, and then the differential of a function, and then the symmetric two tensors on the function. I mean, as a general rule, you cannot split the two jet in any. Well, I mean, you can split it, but it's not canonically splittable under the diffeomorphism group. But once you have a Romanian metric, you can do it. Okay, so that means that, in particular, sim2 of t squared x can now be, since we have this almost complex structure, we can reduce sim2 into the real multiples of the identity, the traceless Hermitian symmetric part, and the skew symmetric part. And everything that I just described goes over. So in particular, there are two things that are, well, I guess I should say that if you think about the theory of plurisubharmonic functions in several complex variables, there are a lot of theorems, right? And many of those theorems go over to this case. I'll just give you two examples. For example, I'm on one of these Grumoff manifolds. I can talk about the Lagrangian Ho of a compact set. What's the Lagrangian Ho? Well, it's the set of points where for every Lagrangian plurisubharmonic function, the value at that point is dominated by the sup over the set itself. Okay? So this is exactly, if you do this instead with plurisubharmonic functions, you get the holomorphic Ho. And now the following turn out to be equivalent. You can say that the manifold X is convex. Well, yeah, I said convex. If for every compact subset in X, its Lagrangian Ho is also compact, right? That's one of the intrinsic definitions in plurisubharmonic theory. Well, that's equivalent to the fact that there exists a log plurisubharmonic function, which is a proper exhaustion of the manifold, okay? And there's also a notion which is like reality. A submanifold is said to be free if it has no tangent Lagrangian planes. And this is always true if the dimension, this should not be X, that should be M. If the dimension of M is less than N, then this is always true. So every submanifold of dimension less than M is always free. And the point is that if M is free, then small tubular neighborhoods, where the distance to M is less than epsilon, are always Lagrangian convex. The boundary is convex, and there exists a log plurisubharmonic function on it. So there are lots and lots and lots of Lagrangian subharmonic functions in log convex domains in one of these manifolds. And let me just say that the Dirichlet problem in this general context, not only for the homogeneous Lagrangian Monge Ampere equation, but for the inhomogeneous one, where the right-hand side is a positive function, can be solved on log convex domains on any Grumoff manifold. So there are lots and lots and lots of these things. And it would be nice if somebody could see another way that they come up. All right, that's all I have to say.
Thank you. Any questions for Blaine? Well, I have one question. Are these elliptic equations that are regularity theory for the homogeneous, for the inhomogeneous case?
The inhomogeneous, well, I mean, like C11, yeah, that probably is true, but I don't know it. But it shouldn't be much more than that, I would think. You know, as it isn't true for the Monge Ampere, so, yeah.
Just to make sure I understood the definition, the only way a Grumoff manifold isn't a Kähler manifold is that the complex structure is not necessarily integral.
I'm sorry?
The only way that a Grumoff manifold is not necessarily Kähler, if I understood, is that the complex structure is not necessarily
Yeah, that's right. That's right. So it's kind of, you keep the Kähler condition, but J is terrible.
If there are no more questions, let's thank the speaker again.
Thank you.